Okay, today we are going to do a couple examples from 1.2, which is the slope of a curve at a point. So you've already read this section, and thus you know that when we talk about, whoa, sorry, my line there. I really should let's just do this the right way. That's so much better. We know that the slope of a curve then is really just so that we know that the slope of a curve at a point is equal to the slope of the tangent line at that point. So remember what slope is just rate of change. How fast is something increasing or decreasing? And of course, these are at the point. So sometimes maybe, let's say, maybe we're going to be graphing our distance from Rock Springs to Rollins versus time. So if we want to know our rate of change, how fast are we going? How fast are we driving? If I could find the slope of the tangent line at a certain point in time, that would tell me how fast I'm going. That's why we care about slopes of tangent lines. And we're going to see later on how to actually find them. But for our first example today, let's find, or let's estimate, let's say. We're going to figure out how to do this perfectly, but for now, let's estimate the slope of the curve y equals 1/4 x cubed minus 2x at the point 2, -2. So again, I have to give you a specific point to find the slope of that curve. Notice if you put in 2 for every x there, of course you get -2 out. So let me show you really quick what the graph of this looks like. So this is my curve right here. Let's just throw it right here. This is my curve, so this is 1/4 x cubed minus 2x, this red curve right here. And again, I don't know what this stands for. Maybe it stands for, time versus distance, or maybe time versus price. But there are a lot of things that we would care about, why we would want to know the rate of change at a specific point. And so more importantly, what we care about right here is at this point, 2, -2. So if I look at this, and let's say I grab a different color here, and I'm going to try and do this. I want to estimate basically the slope of the curve at this point. So what I need to find is the slope of the tangent line. So if I can kind of estimate what a tangent line might look like here, I could take a line and draw it through. And if you notice, if I could find the slope of this green line right here, if you notice it's a tangent line to the curve, then I would say that that is the slope of this curve at 2, -2. And so we can pretty easily estimate the slope of this line. If you notice, let me grab another color here. To find slope, remember the slope of a line is just the change in y over the change in x. So if I look at, let's go from this point to this point. Let me get a color that you can actually see. That might be helpful. How far up would I need to go over? So I went up 2 units, and I went to the right 2. So notice I'm putting a +2 on both of those. So what is the slope of the green line? It would be 2. That's this 2, right? Because I want to do the change in y first over the change in x. So I would have 2 over 2. So I would estimate the slope of this curve to be 1. And based on whatever my x coordinate, whatever my x and my y stand for, maybe this would be distance, for example, versus time. And if I look at distance versus time, maybe I went 2 miles in 2, I was going to say 2 hours, but that'd be sad. So let's say in 2 minutes. So what is my rate of change? It's 1 mile per minute. That's what we would estimate our rate of change or our slope of that curve to be at that point. Now, if I actually look at this, let me show you. Here's my graph, and this is actually what I graphed it on. I'm going to add a function really quick. We are going to figure out how to find the actual equation of this line, but I know what that equation should be. It should be x minus 4. And if you notice, what is the slope of this line, x minus 4? Sure enough, it is 1. So the slope of this green line is 1. That means that the slope of this curve, we define the slope of this curve at the point 2, -2 to also be 1. Let's look at one more example. So what I want to look at is this example here. And this example is actually from the fun sheet. So remember the fun sheets, I have a fun sheet for almost, it's not a worksheet, it's a fun sheet. I have a fun sheet for almost every section of this course. And if you go into Blackboard, there's an actual fun sheet tab, and you can look under the fun sheet tab. You can get a blank copy of the fun sheet, and then you can also look at the solutions. So I have the solutions up for this problem, but I wanted to maybe talk about this and then we'll call it a day. So this is number 3 from the 1.2 fun sheet. The federal debt is the total amount of money owed by the U.S. federal government. So the graph below shows the federal debt in trillions of dollars. Okay, so this is trillions of dollars, right, on the y-axis for the years 1940 to 2004. Approximate the annual rate. So here the x-axis is time. And if you notice, this federal debt then is clearly not linear. So it says approximate the annual rate of increase. So what do they mean here by this rate? Annual rate of increase. So a rate, that would be money over time. That is what it's asking for. Okay, your rate of increase. How much money are we increasing over that amount of time? So we want to kind of see what's the instantaneous rate of change. How fast was my debt increasing in 1990? How fast was my debt increasing in 2002? So now this is not going to be perfect when you do this, and that is okay. So I'm going to look between 1986 and 1992, and I'm going to kind of estimate, well, where is 1990? Let's say it's right about there. And I am going to draw, so I'm going to kind of look at, okay, well, I'll come up here and I'm going to estimate this point right here to be 1990. Okay, so the actual coordinates for this point then will be what? 1990, that's going to be my x. Okay, and what will my y be? Well, if we come across here, and again, this is not going to be perfect, but that's okay. What in life is perfect, right? This is 1.8. Let's say that maybe that's 3.8. You know, I don't know. Let's just estimate in here. I'm not going to worry too much about it. Let's say that's about 3.2 maybe, okay? I'm a little closer maybe to 1.8 than I am to 3.8. So let's say that our debt in 1990 was approximately $3.2 trillion. And so what I want to do then is I actually want to graph a line and estimate the slope of the line at that point. And we'll just do 1990, and then I'll let you look at the solutions and I'll let you try to do 2002. So again, I'm just going to kind of estimate what the slope of this line is. This is going to be a little difficult because, you know, this isn't perfect. And I am going to keep going because what I want to find the slope of this green line right here. To find the slope of the line, what do we need? A minimum of 2 points, correct? So I'm going to estimate the slope of this line. I care this slope. This is the closest that the slope of this line matches to the blue curve. And I notice that I can find another point on the graph, or it doesn't even have to be on the graph. I mean, you can just estimate any other point on the line. Like, for example, let's just say I grab this point right here. And the reason I'm grabbing this point is because I know that it lies on 1992. So I know that this purple point right here has an x coordinate of 1992. Sorry, that's a little tough to see, isn't it? Let's get a little brighter here. And then I'm going to come over and I'm going to estimate, you know, at 1992, it was maybe right about here. And let's just estimate that that point right there is maybe 3.6. And this is going to look different than what I did on the actual solutions because I'm estimating a little bit differently than I may have on the solutions, but we should get something pretty close. I also know, what can I tell by this line? That my rate, right, of increase, it's going to be an increasing number, it's going to be a positive number. So in 1992, I'm going to estimate that my debt was 3.6 trillion. Okay, I'm sorry, not that my actual debt was 3.6 trillion, that on this line, on this green line, that point is 1992, 3.6. So how do we find slope then? Let me find a different color here for you. So we know that slope is change of y over change in x. So I'm going to take 3.6 minus 3.2, all divided by, got to use 1992 first on the bottom, 1992 minus 1990. So what is the slope of this green line right here? Again, that's what I'm trying to find, the slope of the tangent line. That'll give me the slope of the curve. So that the difference on top would be 0.4. On the bottom, I think I can get 2. I could do this one in my head, look at that. So that'd be 0.2. And what are the units on that? So that would be, that would be $0.2 trillion. I know I forgot an I. Again, I'm a math teacher. All over 2 years. So if I wanted to estimate that, or what would my answer be then? So if I want to know, approximate the annual rate of increase, so in 1990, my annual means 1 year, rate of increase is $0.1 trillion per year. So at that moment in time, my debt is increasing at a rate of $0.1 trillion per year. I hope that makes sense. And then if I wanted to come see 1992, well, if you look at 1992 here, I would probably estimate, what do you think? Do you think it'll be greater than, do you think it's increasing faster than it was in 1990? Do you think it's increasing a little more slowly? Well, if this is 2002 and I drew my tangent line here, that's a line, notice that this line isn't quite as steep as the green line. So when I go to find 2002, I would estimate that the annual rate of increase is a little bit less than $0.1 trillion per year, but as I get past 2002, clearly it starts increasing more quickly. Okay, thanks. Work on that fun sheet, work on the homework, and as always, please email me or call me if you have any questions.